Today, greenhouse gases and their emissions are something that we face in our modern world. They're responsible for the enhanced greenhouse effect and are a major contributor to climate change. Net zero is considered as the route to restore balance to our climatic conditions. This involves taking action to both reduce our emissions and capture them. In order to know how we're doing on the emissions front, it means we need a way of measuring each gas, understanding where they come from, and knowing what each one does. Setting limits on each means we also need to know how much impact a greenhouse gas has relative to another. This is where a standardized metric comes in, allowing us to compare each one with respect to a reference gas. This is known as the global warming potential. The GWP specifically tells us how much heat a greenhouse gas will retain within our atmosphere compared to a standardized value. In basic terms, how good a gas is at taking on and then holding on to the heat it's exposed to. So, what's the standardized value we compare each of these gases to? Carbon dioxide, or CO2. This makes sense given it's probably received the most attention out of the known greenhouse gases, on top of it being the one we emit in the largest quantities. With carbon dioxide acting as this reference gas, or standardized value, it's simply set as 1. Knowing that CO2 has a GWP value of 1, we can bring in another greenhouse gas to compare it to. Let's take nitrous oxide, N2O. The latest data from the IPCC states that nitrous oxide is able to retain 273 times more heat within our atmosphere than CO2. This gives us a GWP value for nitrous oxide of 273. This means that for the same mass of those two gases, carbon dioxide and nitrous oxide, the same quantity of N2O can hold on to 273 times more thermal energy than carbon dioxide. Okay, we figured this part out. However, we're not quite done with GWP yet. Time is also a factor, because some greenhouse gases will hang around in our atmosphere for longer than others, meaning they're holding on to that heat in our atmosphere for different lengths of time. What this means for GWP is that you'll most often see it expressed as the GWP 100. The 100 represents the length of time, as measured in years, telling us that the value is based on how much heat is being radiated by the selected gas over a 100-year spell. To keep it simple, carbon dioxide still holds steady at a value of 1, regardless of the time horizon being considered. The GWP 20 is the other common value, with a 20-year period considered instead. Because of the atmospheric lifetimes associated with each gas, this can shift the end GWP value. Taking another greenhouse gas in the form of methane, CH4, the GWP 100 is nearly 30, while the GWP 20 value is much higher at 82.5. The reason for this divide is because methane has a typical lifetime of nearly 12 years. This is why the GWP20 will show us greater impact over the 20-year timespell, whereas the GWP100 essentially dilutes and spreads out this impact over a longer time frame, telling us that less heat is retained when split up over the longer period. And that's it. The GWP. A simplified metric to understanding an individual greenhouse gas's impact over a defined time frame.